Now that we've gone through the basics of analyzing a beam, in this video we will apply our newfound knowledge to study what happens during three-point bending tests. Three-point bending tests are commonly used to assess the mechanical properties of brittle materials. It can prove very difficult to test these materials with a standard tensile test, while three-point bending specimens are relatively easy to prepare, test, and analyze. Three-point bending tests are usually conducted on rectangular beams. These beams are placed on two roller supports, and the load is applied via a third roller, typically mounted halfway between the supports. As a result of this bending, a tensile stress is developed in the material on the convex side of the beam, while compressive stress is generated on the concave side. The first step in analyzing this test method is to convert our setup to its appropriate free body diagram. I have replaced the central roller with an applied load of F, and each of the supports with forces of F over 2. By now you should be able to easily solve for these support reactions by placing the beam in static equilibrium. Once the free body diagram is in place, we can begin to analyze the two unique regions on this beam, region AB and region BC. In region AB, I will place an imaginary cut a distance x from point A. On the face of this cut, a moment and a shear force will be required to ensure that the beam remains in static equilibrium. Note that I have drawn the shear force and the moment in the positive direction according to the sign convention discussed in a previous video. Once we have identified the potential internal loads, we can use the equations of static equilibrium to determine their magnitudes and directions. In this case, we can see that in region AB there is a constant shear force of magnitude F over 2. Also, there is a moment that varies linearly from 0 at point A to 1/4 FL at the center of the beam. Next, we can carry out the same analysis, but this time we'll take a look at region BC. In this case, I place a cut between points B and C that is also located a distance x from point A. And once again, we know that on the face of this cut, we require a potential shear force and moment in order to keep the beam in static equilibrium. In this region, we see that there is once again a constant shear force, but this time it is negative F over 2. And we now have a moment that linearly decreases to 0 when x is equal to L. Now, an easy way to summarize these results is to present them in the form of shear and moment diagrams. Once in this form, it is easy to identify where the maximum moment occurs, and as a result, where the maximum bending stress will occur. Using the bending stress equation, and the knowledge that the x-axis runs through the centroid of the cross-section, we know that the maximum stress occurs at the top and bottom surface of this beam. We can calculate this stress by inserting the value of the maximum moment, FL over 4, the distance from the neutral axis, plus or minus h over 2, and the area moment of inertia about the z-axis, 1/12 bh cubed, into our stress equation. Furthermore, this equation can then be simplified into a much more usable form. One way the stress can be experimentally determined is to mount strain gauges to the surface of this beam. Then we can use Hooke's law to relate the recorded surface strain to the applied load and specimen properties. While this is a relatively easy test to set up and analyze, there are some drawbacks to using three-point bending. For one, the roller used to apply the load also causes a stress at the point of application, and this can cause premature failure. This risk is amplified by the fact that the point of application occurs exactly where the peak bending stress is also generated. It may also prove difficult to place a strain gauge exactly at the point of maximum stress, a matter that is complicated by the fact that there is non-uniform strain on each side of the applied load. Finally, as you are learning in your Science of Materials course, failure is initiated around small defects within materials. By having a very narrow window where the maximum stress is present, the recorded failure values are highly dependent on the state of defects at that particular location, which may not be representative of the bulk material. It would be very beneficial if we could use a setup in which there was a large region of uniform stress that we could easily measure. And for that, you'll need to take a peek at the upcoming 4-point bending video. I know you're excited.